Hi everyone and welcome to this example video. So in your theory lectures you already got familiar with branch cuts and branch points, and you also saw that log is a multi-valued function, that is log of z, where z is a complex number. And today we're going to see some examples on why we care about this branch cut. So before I start the examples, let me try to give you a small motivation. So if you have some x that is a real variable, then you can write this kind of thing. That is, if you have a log x cube, you can write it as 3 log x, right? This is always true when x is a real variable. But if z belongs to the complex numbers, this is not always true. That is, log z cube will not always equal to be 3 log z. Not true always. And this is the thing that makes the complex logarithmic functions really interesting, and now we want to see some examples of it. So let's first start with our example 1. So recall that the principal branch for the log function was defined as log of z will be equal to ln r plus I theta. Let's write a p over here to denote that this is our principal argument, and we had a condition that was r greater than 0 and theta p is bounded by this. So in some textbooks and other literature, people also sometimes don't write this p, because this theta, as you saw that in your theory lectures, that in simple terms we called the principal branch that involved no circuit rotation, that was n equals to 0. So keeping out this p is more of a general notation. So the way to recognize that this is indeed the principal branch is to look over here. So you should always look over these conditions after you are given the functions to determine what to do with that function. So we're going to use this principal branch to show that log I cube is not equals to 3 log I. And let me show you how this can be done. So let's start from this guy, the left hand side guy. So let me just use another color. So this is my left hand side. This is equals to log I cube, which can be written as I square. That is, I cube is just minus I, because I square is minus 1, and let's use that to our advantage. So this is minus I, and this minus I has what? A modulus of 1, that is r equals to 1. So in the next line we're going to write ln 1 plus, you have your I over here, and since this is the principal branch that we're working with, you can see it from here, that is the bound on the angle. We just have to take the principal value, that is the case that will correspond to n equals to 0 that you saw in your past theory lectures. So if you just do that, for minus I, the principal argument is just minus pi by 2, right? Okay, ln 1 is 0, so that is 0 over here, and it will be, the final result is I pi by 2, and there is a minus in front. So this is our left hand side. And now what we want to do, we want to go to the right hand side and evaluate it. So let's just make a phase boundary over here so that we don't get confused, and we can compare our results side by side. So now to evaluate the right hand side, we'll start with 3 log I, right? 3 is just there. Log I will also have the following form like this. So let me just put a bracket so that you don't get confused. This I will have a modulus of 1, so the R is equals to 1, so you'll have a ln 1 over here, but I lies on the positive y-axis, that is the principal argument over here will be just plus pi by 2, right? Okay, so let's write that. We have our imaginary term over here, and the principal argument is just plus pi by 2, and ln 1 is 0 again, so this is just 3 pi by 2 multiplied with an I. And you can see that left hand side and the right hand side, they are not equal. So you can see that the left hand side is not equals to right hand side. So we can say log I cube is not equals to 3 log I when we have the principal branch. So this is why we care about these branch cuts, because it will depend on which branch you are working. And in fact, let me show you another example, and this will be our example 2. And here we have to show that log I squared is equals to 2 log I. But here they are giving us some conditions, that is r greater than 0, and my angle is bounded by this. Note that this theta is not the principal argument. So how can we write this thing, right? Because and you might be confused with this theta, because sometimes we are using the principal argument, sometimes we are not. So let me just tell you, in general, we should always go for log z as ln r plus I times theta principal plus 2 pi I. So if you don't want to write that, and most of the time people don't write that, so it should be ln r plus I theta, where theta is defined as, so let me put it in a box since this is a side note only. This theta is just theta principal. So this is our principal argument, and this is the whole theta, and there will be a 2 pi n. Again, recall n was 0, plus minus 1, plus minus 2, and so on. So here you have a boundness on theta, that is this theta over here. And the bound, let me just write it again, pi by 4 theta 9 pi by 4. And you can guess that here theta is actually positive. It should be positive, that is, it's bounded on the lowest side, or bounded below by pi by 4. In fact, not pi by 4 is exclusive here, not inclusive. And the upper limit is less than 9 pi by 4, and this 9 pi by 4 is just slightly greater than 2 pi, right? And this condition over here, it will help you to prove it. So this condition will help us to prove it, and it will put restriction on n, that is this n that is appearing over here. So let's see how this comes. So the first thing we need to do right now is that let's try to write our left hand side. So let's call this the left hand side. We'll proceed as before. we have log of I squared. This can be written as log of -1, which is just ln 1 because it has a modulus of 1, and I, this is a -1, right? So the principal argument is what? Pi, because it's on the negative x-axis, right? So this is just pi, and we have our 2 pi n. And now again we can recall that the condition that we had was theta, which was just the principal argument plus 2 pi n, it should be bounded by pi by 4 theta and 9 pi by 4. This was the bound. So let's see which kind of n, that is what values of n, because we have n as 0, plus minus 1, plus minus 2, and so on. So what kind of n satisfies this bound? So let's take n equals to 0 first. If you take n equals to 0, okay, we can simplify it more. This is just I pi plus 2 pi n, because ln 1 is just 0, right? So when n is equals to 0, left hand side is just I pi. What if n equals to 1? When n is equals to 1, left hand side is 3 pi I. But this is violating this bound, right? So we can say that we don't need n equals to 1. And if n is equals to -1, we are getting the left hand side as I pi minus 2 pi n. This is just minus pi I. This is also violating this bound. So the only valid value for n for the left hand side that satisfies this bound is just n equals to 0. So we can safely say the left hand side will be just I pi. Also you can write with n equals to 0. 0 that satisfies the bound on theta. Or you can also explicitly write it as theta principal plus 2 pi n. Understanding this is just the important thing, but you can choose whatever way you want to write. Now let's inspect the right hand side. So the right hand side is just 2 log I, right? So 2 log I. And again, proceeding as before, it's ln 1 I, our theta principal plus 2 pi n. I'm just writing it symbolically and I'll put the values soon. So 2 ln 1 is just 0, 2i. This is just I, right? So I is just over here, and the principal argument is just pi by 2, or plus pi by 2 to be exact. So this is plus pi by 2, and we have our 2 pi n. And again, the bound that is for theta, which is theta is equals to theta principal plus 2 pi n, we can write the bound again to remind ourselves that we should satisfy this bound, and we want to see whether the thing we wanted to show is actually true or not. So let's again start with n equals to 0. When n equals to 0, the right hand side is just I pi. When n equals to 1, the right hand side again will be, this 2 and this 2 will cancel out, so it will be n equals to 1. Let me just write down the rough work. It will be I pi 4 pi dot 1, because I'm putting n equals to 1. So this is 5 pi, right? So this is 5 pi I. And if you look at this bound over here, that is the thing that will be our main concern. This is violating the bound, so we don't need it. We don't need n equals to 1. Again, we can go for n equals to -1, and if we do that, the right hand side will be just 2i pi by 2 minus 2 pi. And here you can see that this will be I pi minus 4 pi, right? And this is just minus 3 pi I. So this is also violating this bound over here. So we don't need n equals to -1 as well. So the only valid n for that satisfies this bound is also n equals to 0. And for that we have the right hand side as I pi as well. And if you just check the calculation above, this left hand side is I pi with n equals to 0 that satisfies our bound on theta. and same goes for the right hand side. So we can write finally that left hand side is equals to right hand side. That means in this case log I square is just 2 log I. So you can see that this whole equations or this relationships are actually coming from the region that we are bounding, or the constraints on the brackets that we are imposing on these functions. So this is the reason why branch curves are important, because we cannot write this kind of relation to be true always. And this will be it for today, and thank you.